Heads again? That's 70. 71? Holy cow, 72?
72 what?
Oh, you're not going to believe this, Pete. I've been flipping this quarter, and it's come up heads 72 times in a row.
Wow, really? That is highly unlikely.
You don't say. It's also highly suspenseful. I mean, how long can this go on?
Heads again, 73.
And it's really moving me to re-examine my face. If in nothing else, at least in the law of probability.
Okay, Rosencrantz. I said it's highly unlikely, but it's not completely against the laws of probability.
First of all, Pete, I'm clearly Guildenstern in this scenario. And second of all, what are the odds of 73? Wait, hang on a sec. 74 heads in a row.
Well, that'd be 1/2 times 1/2 times 1/2 and so forth until you've multiplied 74 of them together. So your odds are 1 in almost 19 sextillion, which is the number 19 with 21 zeros after it.
So this kind of thing doesn't just happen. It must be indicative of something.
Like what?
Okay, a list of possible explanations. 1. I'm subconsciously willing the coin to land on heads every single time.
Oh, so now you're Guildenstern and Magneto. What else you got?
Okay. 2. Time has gone completely wonky, and we're just seeing one single coin flip being repeated over and over and over 74 times.
Oh, yeah, gotcha. Scratch Magneto. Now it's Groundhog Day.
It could be, Pete. It really could be. Wait, did I already say that?
Next.
3. Divine intervention.
Oh, like some supernatural deity with omnipotent powers. They've got nothing better to do with their day than make sure you flip heads a whole bunch of times.
It could be, Pete. It really could be. I did say that already.
You know what? Knock it off. This is just how probability works sometimes. Even though the odds of this happening are infinitesimally small, they're not zero. And that means, unlikely as it is to flip 74 heads in a row,
75.
and as unlikely as that is, it's still possible to have it happen without mutant powers or time loops or deus ex machina.
I guess.
To tell you the truth, Noah, even when a coin is flipping exactly as expected and landing tails just as often as it's landing heads, you can still get some situations with pretty counterintuitive results.
Oh, yeah? Like what?
Well, I could think of several examples, but why don't you continue your incredibly amazing run of heads until it ends, and then meet me in the studio so we can talk about my friends, Alice and Bob.
Oh, yeah, sure. Just give me 1 second. There, tails.
Maybe there's really something to your Magneto theory after all.
Head you win, tails I lose. Head you win, tails I lose. Bad news.
Hey there, Math Club, and welcome to another exciting episode of the podcast. Actually, this is a very special episode, Pete. Do you know why?
Well, I'm here, and every episode with me in it is pretty special.
Well, that's true, but I was talking about the fact that this is episode number 50.
Oh my gosh, really? 50 already?
Yeah, it seems like just yesterday we were on episode number 49.
I think that was like last week, but I get your point. It's been a good long run.
It has, so happy 50. And what have you been up to recently?
Well, as our listeners might have guessed from our opening sketch, I've been thinking about coins and flipping a whole bunch of them.
Well, I've always said that you're flippin' brilliant.
Well, thank you very much. So, as you know, I'm a fan of Twitter, and I follow a bunch of people on Twitter who are either educators or mathematicians or math educators. And one of the people who I follow is an assistant professor of mathematics at the University of Toronto. His name is Daniel Litt, and he frequently posts these really interesting probability puzzles. And he's got quite a following of folks who love to dive in there and kind of talk it through.
And is one of these puzzles about the odds of flipping 75 heads in a row?
Well, not exactly 75 heads in a row, but here, I'll tell you what. Why don't I just read the problem statement directly from Daniel's tweet?
All right, let's hear it.
Flip 100 coins labeled 1 through 100. Alice checks the coins in order 1, 2, 3, and so forth, while Bob checks the odd labeled coins first, then the even labeled ones. So 1, 3, 5, all the way up to 99, and then 2, 4, 6, and so forth till he's done. Here's the question: who is more likely to see two heads first?
Okay, well, first I want to make sure I understand the question. Do we mean two heads in a row, or do we just mean two heads at all?
Just two heads at all. So a total of two heads as you're going along checking the coins.
Okay, well, so it looks like Alice is going to be looking at all 100 of them in sequential order. Bob is also going to be looking at all 100 of them, but in a different order. But each of them are looking at 100 coins, and each one of those flips is just as likely to be heads or tails. So my initial instinct on this would be that they are both equally likely, that there's no reason either one of them should have an advantage in unveiling their second heads before the other.
Well, what's interesting is that Daniel actually included a poll as part of the tweet, and the choices were Alice, Bob, equally likely, or don't know slash see results, right? So if you didn't have an opinion or you didn't want to express an opinion, you could just click that to see what the results were. So I actually made a choice and submitted my answer via his poll.
What was your choice?
The wrong one.
Wrong!
The same wrong answer that you gave just a moment ago.
Okay, so it also seemed to you like there was no reason either one of them would have an advantage in finding two heads first.
Well, as you know, we've talked about this before. My intuition around probability is that's not my strong suit. I did believe when I read this problem that the answer couldn't possibly be equally likely. And yet, on the other hand, I was like, well, that does seem, as wrong as I believe it to be, it does seem like the neutral answer, right? I don't know. Is Bob or Alice more likely? It's hard to say. So I was like, I'm just going to go with my initial wrong intuition, and I submitted equally likely. Now, it turns out that I was not alone in the poll in choosing equally likely, not by a shot.
Do you remember what the breakdown of the results was?
Yeah, in fact, I don't have to remember. I'm looking at them right now. So check this out. There were 14,682 people who voted on this poll. That's a pretty large number. And 69.3% of them selected equally likely. So the vast majority. A small handful, 12.9%, chose don't know, see results. 11.4% said Bob, and only 6.5% said Alice. So I, along with I don't know, 7 or 8,000 other people got this problem wrong.
And if it makes you feel any better, you might remember that I would have been right in there with you if I had answered this poll.
Ah, thanks, chum.
That's what friends are for.
Now, I have a question for you before we go on. You said a minute ago that even when you put in your answer, you felt pretty strongly like that couldn't possibly be the answer, that it couldn't possibly be equally likely. Is that because you had some sort of mathematical hunch, or is it just because you were thinking there's no way Daniel Litt would have posed this problem if the answer was the obvious one?
Well, there are a couple of things. First of all, I have done enough probability and I have seen enough of it go in these, sort of interesting sideways ways. And I have seen, strange results. So that was in the back of my mind. The other thing that I think is worth noting is there's definitely some asymmetry in the approach that both Alice and Bob take. Alice goes in order. Bob goes 1, 3, 5, skips over the evens, then circles back. So anytime there is an asymmetry in a situation that otherwise appears to be probabilistically equal, that's a clue that you shouldn't expect the answer to be equally likely. And also, I've read enough of Daniel's tweets to know that, yeah, there's always some interesting twist.
All right, Pete. So enlighten us. Who is more likely to get their second heads first?
Well, I decided to write a little simulation. I wrote a little Java program that runs many, many trials of this experiment and then reported on the results. And so, would you like me to tell you who the winner is?
Actually, I want you to wait a second because I love that idea and I want to write my own simulation. I'm going to do it in Scratch, which is a coding environment that I know and I use with my students a lot. So, how about you give me a few minutes to code it up and then we meet back here and I tell you what I got and you tell me if it matches what you got.
Sounds good.
All right, Math Club, you stay where you are because as far as you're concerned, this trip is going to be instantaneous. All right, Pete, we're back. I have finished my simulation and here are my results. When I run the simulation 100,000 times, Bob wins about 42% of the time. Alice wins only about 31% of the time, and they tie about 27% of the time. How does that compare to your Java simulation results?
Well, guess what? That's very close to what I got. With 100,000 trials, I'm showing that Bob wins approximately 41.5% of the time. Alice wins approximately 31.2% of the time. And the remaining games are a tie, coming in at just about 27.2% of the time. So looks like Bob is the winner.
Yeah, well, first of all, I'm impressed that both of us coded our own independent simulations and our results came out so close to each other. I think that means both of us did it right.
I'm impressed that you got the same answers I got, since after all, I've been a professional software engineer for more than a decade.
All right, well, maybe it's not impressive that you did it right, but I'm impressed that my answers matched your answers. How's that?
Okay, I'll accept that. Actually, I think it's really cool. We use two very different tech stacks. We use two totally different frameworks. We both came up with the same answer. I think that's an encouraging sign that suggests, yeah, I think we're probably onto something.
I think you're right. But what I have zero idea on is why is Bob more likely to win?
Why, Mr. Anderson? Why? Why?
I mean, they're both just looking at 100 random coin flips. They're just looking at them in a different order. Why would Bob be more likely to win than Alice?
Yeah, that's a great question. I think, who's more likely to win is one thing, but I really think what we care about is why. Now, I can think of three different ways that someone might go about trying to answer that question, trying to shed some light on that. And here they are. One, by generating empirical evidence.
That's kind of what we both just did with our simulations, right?
Exactly. We conducted some trial runs, we gathered the data, and we analyzed the results. And, in a lot of ways, that's a classic scientific approach to a problem, right? You want to test out a hypothesis. So you run a bunch of trials and you analyze the data that you get.
Okay. But while that method gives us the what, it doesn't really give us the how or the why, does it?
Right. So my second approach then would be to think my way into a plausible explanation. Try to come up with some framework of understanding that sheds light on this particular scenario.
And when you ran it through your big math brain, were you able to come up with a plausible explanation?
Well, I'll tell you what, let's take a step back and see if we can kind of work through that together. Because, there's one particular tool that I like to use when we're talking about math. I've used it several times on the show, and I kind of want to apply that tool right now.
Is it a hammer?
Stop.
Hammer time. Go with the flow.
It's not hammer time. No, it's a tool that you look at the numbers in the problem that you're trying to analyze, and you find ways to change them to kind of simplify the scenario down to something that is more manageable. And in this particular problem, there are two parameters that we could play with.
May I guess what they are?
Please do.
Well, one of them is probably that big number, that 100, the number of times that we're flipping the coin. Is that one of the two variables you're thinking of?
Absolutely. We could ask, well, what would happen if far fewer coin flips were being considered. And I think we should do that. Do you want to guess at the second one, though?
Well, the only other number that really comes up in this problem is the number 2 in terms of who gets 2 heads first. So I'm guessing it's how many heads it takes to win.
Yeah, we could also play around with that number. So let's go ahead and start with the number of flips. Let's kind of reduce that down to some minimal case and see if by looking at these smaller problems, we can generate a plausible explanation.
Okay, that sounds fun. Let's do that. How many flips do you want to reduce it down to start?
Well, it seems to me like if we're going to require 2 heads for a win, we kind of can't go below 2 coins. So what if we start with 2 flips?
All right. So we're flipping a coin twice. And what do we do?
Well, first of all, notice that there's a specific pattern that Bob follows when there are 100 coins. First, he looks at the odd ones, then he looks at the even ones, and he finishes. So we can't say, oh, with 2 coins, Bob should first look at coins 1, 3, 5, 7, 9, all the way up to 99, because we don't have that many coins. So instead, we just follow the recipe. First, Bob looks at the odd coins in order, and then he looks at the even coins.
Okay, but when I picture what that's going to look like, in this particular case, since there's only one odd flip, flip number 1, and one even flip, flip number 2, aren't both Bob and Alice going to be looking at those flips in the exact same order?
Yeah, they are. So here, when we reduce the complexity of this problem by taking 100 flips all the way down to 2 flips, we've actually collapsed the distinction between their behaviors. And now we see in this case that they're going to behave exactly the same. So who's more likely to win in this scenario?
Well, in this scenario, they are equally likely to win every single time because they're looking at the coins in the exact same order.
Right. So in this scenario, either the 2 flips are heads, heads, and they both win. It's a tie. Or we get 2 tails, tails, heads, or heads, tails. And in all 3 of those variations, there is no winner. They don't even tie, really. And I guess they both tie for second place.
So with only 2 flips, the answer is that neither one of them is more likely to win.
Right. So we're not able to really shed light on our problem. In this case, we better up it to, let's say, 4 coin flips.
All right. So with 4 coin flips, there's going to be 16 possible outcomes. Is that right?
Yeah. And now Alice and Bob will look at those coins in 2 different orders. So that's good. That's a step up from where we were when we only looked at 2 coin flips.
So to make sure we all understand this, Alice is going to look at flip 1, then flip 2, then flip 3, then flip 4. And Bob is going to look at flip 1, then flip 3, then flip 2, then flip 4. Because he's going to look at the odd ones first and then the even ones.
Right. Now, among those 16 different outcomes, I wanted to see where either Alice or Bob was coming out ahead. We know from our code that Bob should come out ahead. I kind of wanted to see that. Well, guess what? Among those 16 outcomes, again, they tie. They're equally likely to win. I actually made a little spreadsheet where I wrote down all 16 of the possible outcomes, starting with heads, 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 and working my way down to tails, 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 tails. And then I looked to see in each of those cases, did Alice win? Did Bob win? Was it a tie? Did neither of them win? And I gathered those numbers together.
All right. And just to make sure I'm sort of understanding where we are here, if we had a scenario where the first 3 flips were heads, 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 we would consider that a tie, right? Because Alice would win on her second coin that she looked at, which would be coin 2. And Bob would also win on the second coin that he looked at, which would be coin 3. Is that right?
Yeah, that's one of the tied outcomes.
However, if they went heads, heads, tails, that would be an Alice win because Alice would win on her second coin, whereas Bob would not win on his second coin. It would have to keep going.
Yeah, so the 2 outcomes that Alice wins on are heads, heads, tails, tails, and heads, heads, tails, heads. The 2 outcomes that Bob wins on are heads, tails, heads, tails, and heads, tails, heads, heads. Aside from those 4 possibilities, they either tie or neither one of them sees 2 heads.
Okay. So it seems to me like both with a sample set of 2 flips and a sample set of 4 flips, our initial intuition that they would be equally likely to win is holding true. It's not until we get up at 100 flips where we're seeing this difference where Bob's pulling ahead.
Well, now remember what we're trying to do. We're trying to see if we can spot an obvious explanation for why one of them would win. And I don't think we need to go all the way up to 100. We know from our code that we would see it with that many flips. One always hopes that you can kind of reduce down to a smaller number and see it sooner. Unfortunately, we're not seeing it for 2 flips and we're not seeing it for 4 flips. So the next obvious example to check is 6 flips. But with 6 flips, there are 64 possible combinations of heads and tails to sort through.
So it's starting to get to a point where this is kind of hard to check by hand, isn't it?
It is, but because I'm fearless, I actually did check this by hand one more time with n equals 6, and I wrote down all 64 of those combinations and figured out how many times Alice wins, how many times Bob wins. And you may say, Pete, why didn't you write some code to do that? And the answer is because I kind of wanted to just get to the heart of the matter quickly.
I've been trying to get down to the heart of the matter.
And I like to verify small cases by hand. I mean, remember, we already know empirically by our code that the answer is Bob is more likely in the original statement of the problem. If I answer these smaller cases with code also, then I'm sort of saying, oh, well, it's empirical. It's the code. Like we still haven't shed light on the problem.
Right. We still haven't said why. So when you did your test on 6 flips, who was more likely to win?
Well, at first, it looked like Bob was more likely to win. And I thought, okay, that's cool. I then did decide to modify my code a bit to double check. And when I ran it, the simulation with 6 flips, it came out equal again. So I went back, looked at the spreadsheet, found the mistake I had made by hand. And sure enough, they actually are still equally likely to win if you do 6 coin flips.
So out of those 64 cases, how many did each of them prove to be the winner?
18 times. So 36 of the 64 resulted in one or the other one of them winning. And then the remaining cases were either ties or neither one of them ended up seeing heads twice.
Okay, so I'm assuming now you upped it to 8 coin flips to see what you would find there, but I'm hoping you didn't do all 256 of those possible outcomes by hand again.
I did not. I made my high school teenager do it. At this point, I finally decided, well, okay, I think I'm going to have to turn back to the code and run the simulation on an 8 flip sequence. And when you do that, you find out that actually Bob is slightly more likely to win.
So you said Bob is slightly more likely to win with 8 flips. Is it the case that as we add more and more flips now, Bob becomes more and more likely to win?
Yeah. And in this case, with 8 flips, there are a total of 256 possible outcomes. Alice wins in 82 of those scenarios. Bob wins in 90 of them. So, he's about 10% more likely to win. And in terms of percentages, Alice wins about 31.9% of the time, and Bob wins about 35.26% of the time.
Okay, so even those numbers aren't that far off from what we saw with 100 flips.
What I think is interesting about this is that the very first time I tried to figure this out, when I learned that I had submitted the wrong answer to the poll, and I was like, all right, well, let me see if I can answer this question for myself. And of course, my first strategy is always, let's reduce the complexity. And so I spent a fair bit of time trying in my head with 4 flips to figure out what was going on. I was picking up my 3rd grader from school and I had some spare time waiting for him. And I was just thinking about this. Well, it wouldn't have mattered how long I thought about it, because in the end, when you've got 4 flips, they're equally likely. That wasn't going to ever shed light on the problem. And the same with 6. But what I think this is telling us is this is part of why this problem is intuitively tricky, because when you actually do the math for the first several cases, there is no difference. They seem like they're equally likely.
They don't seem like they're equally likely. They are equally likely in those opening cases, right?
Yeah, and what I meant was it seems like that's going to be the case, that they're not actually going to deviate and have one of them do better than the other. So it's not until I got to 8 that I saw that there was the difference. And actually, it turns out if you go up to 7 coin flips, you'll see already that at that stage, Bob does have a slight advantage.
Well, I'm glad you said that because I've been wondering this whole time, why are we only looking at situations with even numbers of flips? Why are we skipping the situations with an odd number of flips?
Huh. That's odd.
Yeah, only because it's closer to the original formulation of the problem, right? 100 flips is even, and you say, first, Bob will look at the 50 odd numbered coins, and then he'll look at the 50 even numbered coins. Well, of course, with 7, Bob would just look at coins 1, 3, 5, 7, and then 2, 4, 6. So it's slightly different. I wanted to stay just a little bit closer to the original formulation, which is why I was focusing on even numbers.
Gotcha. But what you did find out was once you get up to 7, that's where Bob starts to pull ahead. But I'm still wondering all about the why. Did you have any insights into what's going on that makes Bob a little more likely to win once we get up into enough trials?
So I started to look at the actual patterns of heads and tails that would result in first Alice winning, or on the other hand, Bob winning. And maybe one could analyze those and find something. But I wasn't really seeing anything. So I went back sort of to basics and I said, well, I could, in addition to having reduced the number of coin flips, I could play around with that quantity that determines how many heads you need to see to win the game.
Okay, well, there's only one number we can reduce it to. Since it was already down at 2, I guess you reduced it to 1.
I did. Now, what I'd like us to imagine is, let's pretend we really are going to flip this coin 100 times, that Alice will look at them sequentially in order. Bob will do this pattern 1, 3, 5, 7, and so forth, and circle back to the evens. But to win, you only need to see heads once. All right. Now, on the first round, because they're both looking at coin 1, either they both see heads and they tie, or neither of them sees heads and we move on to the next round.
Right, gotcha.
On the second observation, Alice looks at coin 2 and Bob looks at coin 3. Those 2 coins are equally likely to have been heads or tails. So therefore, they're either going to win or tie, or either will win with, even odds. There's not really any difference at this point.
That makes sense. So if coin 2 is heads, Alice has got it. And if coin 2 is tails, Alice doesn't have it. Similarly, Bob is looking at coin 3, and if it's heads, he's got it, and if it's tails, he doesn't have it.
So when they make their third observation, what does Bob look at?
Bob looks at coin 5.
A brand new coin that has full probability of potentially being heads. What does Alice look at?
Well, Alice looks at, oh, Alice is looking at coin 3, which Bob already looked at and moved on.
So we already know what Alice is going to get on coin 3.
She's getting tails, because if coin 3 had been heads, Bob would have stopped right there with his first heads.
Exactly. So now, if Bob hasn't won yet, because coin 5 was in fact also tails, they make their fourth observation. Alice gets some new information. She gets to look at coin 4. Bob has not looked at coin 4. She's the first one. Bob also gets new information. He's looking at coin 7. Nobody's looked at it. So we're in this scenario again where the probabilities are even-handed. They're going to win or lose according to whatever those even probabilities are.
I think I'm starting to see what you're getting at. Every other observation where Alice and Bob are both getting new information, they're equally likely to win. But on those ones in between where Alice is looking at a coin that Bob already looked at, she's not going to get to win, while Bob is still looking at a new coin on every single one of those turns and might win.
That's exactly right. In fact, I think that's the insight that gives us our plausible explanation for why Bob is more likely to win.
That's pretty neat. I would never have thought of that without you taking us back through a simpler version of the problem. But now that we've done that, I can totally see why Bob is a little bit more likely to win than Alice is.
Yeah. Now, there are a couple of things that should be said here. One, we did simplify. The original problem does require seeing two heads to win. We reduce that down to one. We got some insight. And so we have to make a little bit of a leap or maybe try to think our way through that scenario. But in effect, the idea is the same. Bob is more likely to win because, at least for the first 50 rounds, he is consuming brand new information on every turn. Alice only gets new information every other turn.
And on the turns where she's getting old information, it's never going to be winning information.
Not never, but it's less likely to be winning information. I think our takeaway here is that when Alice is looking at odd numbered coins, she's less likely to win on one of those steps because Bob has already benefited from any heads that might have been there. Now, I want to add one tiny point here. We reduced the number of heads required to win because we were interested in generating some intuition about how the solution to the problem might go, right?
Yeah.
We could also ask what happens if we raise the number of heads required to win. And there's something very interesting that happens if you go so far as requiring 26 heads to win.
What is it that happens at that point?
Well, I'm curious, thinking about the numbers involved here, is there anything particular about 26?
It's one more than a quarter of the total number of flips. If the total number of flips is 100, a quarter of that is 25, and 26 is just one more. So I'm guessing it has something to do with it needing to be more than one quarter or 25% of the flips.
Yeah. Now, if you think about Bob's strategy of looking at the odd numbered coins, how many coins will he look at before he circles back to the evens?
Well, he'll look at the 50 odd numbered coins.
And of those 50 odd numbered coins, how many of them might we expect to show up as heads?
And that's where we're getting to 25.
That's where we're getting to 25. That's the expected number of heads that we would see in those first 50. And if Bob hasn't won by the time he gets to coin 99, he's got to go back to coin 2. And guess who's already benefited from coin 2?
So now the benefitor becomes the benefitee because now Bob is looking at information that Alice has already burned through.
Bam! That's exactly right. And we see when 26 heads are required to win, suddenly the probabilities switch and Alice becomes the more likely winner.
Wow, that's really neat. I would not have thought this through to that outcome, but that's really cool.
And I think it's just so weird in there that, like, I mean, it makes sense, but I mean, how are you going to just naturally, you walk in off the street, you open up Twitter, you see this problem. How are you going to have this intuition already in hand? It just seems like you're not. You're probably going to get it wrong and click equally likely. I think this kind of gives us what I would call a plausible explanation or a bit of a framework to help our intuition as to why Bob is more likely to win.
Yeah, absolutely. And now that you mentioned plausible explanation again, I remember that that was your second of 3 ways that we might be able to shed some light on this. What was the third way that we haven't mentioned yet?
Well, the third way is, of course, the one that mathematicians would prefer and, in fact, insist upon. And that is an actual mathematical proof that Bob is more likely to win.
Oh, okay. So do you want to do a mathematical proof for this?
I intend to prove beyond the shadow of a doubt.
You know, I don't. If somebody is interested in seeing one, I believe one of the respondents to Daniel's original tweet does link to an article they wrote that kind of gives that mathematical proof of the result, or at least would get listeners quite a bit in that direction. I do want to emphasize one thing, though, about this is that even if we pull together a proof, that doesn't always guarantee that it will boost your intuition. Some mathematical proofs are simply the rigorous confirmation of what our empirical experiment already told us. The very best proofs provide intuition as well. And in this particular example, I'm not sure. I haven't tracked down the details.
And that intuition is a little different than our initial intuition when we were just going based on our gut, because that intuition is after a rigorous proof.
Yeah, that's the thing about the very best proofs is that not only do they confirm the result with mathematical rigor, but they also can provide intuition and insight that is based on a very solid foundation. So if you understand that proof, you will not only really convince yourself that the result is true, but you'll understand why, because the proof is revealing in that way.
That makes sense. So, of the three methods that you came up with, the first one was empirical evidence, which we employed with our simulations. The second one was a plausible explanation, which is what we got to after a little while of talking through a simplified problem. And the third way is a mathematical proof, which we could do, but we're not going to take the time to do right now. But listeners, you can check out a link in our show notes to the original problem, which does reference the proof.
Yeah, and I think what's cool about this is these three potential approaches. Mathematicians often take as their starting point either some empirical evidence because they conducted a simulation, or when you're working in pure mathematics, it's because you've observed a pattern. You didn't like compute anything, but you've observed a pattern by looking at a wide range of examples. And you say, I wonder if this observation that I'm making that is common across these examples is actually pointing at a theorem, at some mathematical result. And so I think this is a nice way to kind of model how mathematicians think. They start off with some evidence of some kind, whether it's intuition or the results of the model or something, and then they take it that extra step to complete a proof. So I'm not myself going to go and track down the proof, but I feel pretty good about this problem. And I'm sorry to say, Alice, but Bob's got you.
Well, Pete, thank you so much for talking through this problem with me. It was really interesting to see where it took us. It's not where I expected it to go when we first started the conversation. And that's one of the fun things about math.
Yeah, totally. And I want to say to listeners out there, please drop by, get yourself on Twitter and go take a look at Daniel Litt's Twitter feed. He's got a lot of interesting probability problems in there. Plus, he talks about interesting mathematics beyond these kinds of puzzles. I think listeners might enjoy what they find there.
And on that note, we're going to wrap this episode and we will see you next time, Math Club.
Take it easy, Math Club.